Alright, this is the second lecture for Text Unit 1. Before we move on to today's subject, let's take a look at something from the last lecture. You should all be able to attempt this quick conversion problem. How many feet are in 13.4 inches? Attempt the problem before you move on to the presentation, and attempt it using the methods of this course, which is to say using unit conversion factors. Here we have the solution. 12 inches is 1 foot. Now, this is true by definition. And this equality, 12 inches, 1 foot, can be a unit conversion factor. In other words, you can convert from feet to inches and inches to feet. So we write down what we know, what has to get converted, 13.4 inches. And then multiply it by a unit conversion factor, which cancels inches. Inches in the numerator here, cancel in the denominator here, and leave units of feet. The answer is 1.12 feet. Any time you have an equality, inches and feet, or any of the equalities from Table 2.1, you can assemble unit conversion factors. You can assemble a this equality will let you assemble a unit conversion factor from inches to feet, or you could convert from feet to inches. All right, now we begin the actual lecture for Unit 1, Part 2. This is the significant figures lecture. You may have been introduced to significant figures in high school. Significant figures are actually about measurement and error. All measurements that including the measurements that you'll make in laboratory courses in later semesters, contain some error. There are two terms used to discuss this error. Accuracy refers to how close a measurement of a value is to the true value. Most people understand the meaning of the word accurate. For example, if I weigh 170 pounds and step on a scale and it says I weigh 387 pounds, that scale is not very accurate. The meaning of precision is generally less clear, and most people actually misuse the word precision, thinking that it's just a synonym for accuracy. Word precision refers to how close two measurements are to each other. Now, this is the formal definition of precision you can see in just about any textbook. What does it mean? Well, I will illustrate on the next overhead. Here's an example of how measuring works, and let this be a sort of tutorial on how to measure in your laboratory courses. Suppose we have a block, which is this black colored object here. You can ask, how long is the block? Suppose to determine the length of the block, we have this stick, which is marked off in centimeters. And as is often the case, the length of the block does not fall exactly on one of the lines. It falls between the two lines. When you have to determine the length of the blocks, provided with an instrument like this, it is up to you, the experimenter, to infer the length or estimate the length between 2 and 3 centimeters. And clearly the block is between 2 and 3 centimeters. This kind of estimating should always be done to the next decimal place. In other words, these numbers are in the ones place, so the estimation should be to the tenths place. So one student might estimate 2.5 centimeters, for example. The next student might estimate 2.6, and another might estimate 2.7. The last digit in any measurement in the laboratory is uncertain. In our example 2.6, for example, the 0.6, or this 6, is uncertain. Might be 5, might be 7. Uncertainty in numbers is expressed and dealt with using significant figures, or significant digits. The significant digits are all the certain numbers in a measurement and the uncertain one. And further, the uncertain one is the last significant digit in the number. What's needed is a set of rules to determine if a digit is significant, and we can discuss that first. A set of rules for determining if a digit is significant appears in Unit 1 of the text, or Text Unit 1. First, all non-zero digits are significant. Second, zero digits between non-zero digits are significant. So in the number 202, all of these digits are significant. And further, this 2 is the uncertain one. The way this number is written implies maybe 201, maybe 203. Zeros at the end of a number are not significant if there is no decimal point. Inclusion of a decimal point in a number indicates these zeros are significant. Okay, so quickly, if we have the number 20, this 0 is not significant and the uncertainty is here. This means could be 10, could be 30. If you have a decimal point, this 0 is significant. There are two significant digits, and this is the uncertain one. This number could be 19, could be 21. Zeros after the decimal point, but before any non-zeros, are not significant in the event there are no non-zeros before the decimal point. So, if we consider the number 0.022, there are two significant digits. The first two zeros are not significant. The expression you may have heard before is that these two zeros are holding the decimal place. In this number, 20.022, the fact there are non-zeros before the decimal place means that all 5 of these digits are significant. The last 2 is the uncertain. Another way of putting this rule, or consequence of this rule, is that if you have the number 20.0, the fact that there is a 2 before the decimal point means that all 3 of these digits are significant, and this is the uncertain digit. So this measurement may be 20.1 or 19.9. Rule E states that zeros after the last non-zero, after the decimal point, are significant. So, for example, the number 0.200 has 3 significant figures, including these 2 zeros. And the number 0.000200 has 3 significant digits, this 2, the following zeros. These zeros again are said to be holding the decimal place. In any number expressed in scientific notation, all the numbers appearing in the argument are significant. So 6.022 times 10 to the 23rd has 4 significant figures: the 6, the 0, the 2, and the 2. The exponent has no impact on the significant figures. This rule means that if this number 1400 is written this way, it has 2 sig figs, the 1 and the 4, as we've seen before. But if the number is written this way, 1.400 times 10 to the 3, the 4 numbers in the argument are all significant figures, and this number has 4 sig figs. It's important at this point to mention exact numbers. Exact numbers are numbers with no uncertainty to them. So, as you might imagine, anything that can be counted is an exact number. If you count 3 apples, there are 3 apples. There is no uncertainty about it. Exact numbers in this course arise from definitions like 1 foot equals 12 inches, or for every equality in table 1, for example, 1 milligram is 10 to the negative 6 grams, or a conversion factor made from that equality, 10 to the negative 6 grams over 1 milligram. This is an exact relation. This conversion factor is an exact number. Exact numbers have infinite significant digits for counting purposes. All right, let's consider some examples. Here are some numbers. Indicate the number of each of the significant figures. You can imagine completing this table. And then let's write these 2 numbers in scientific notation. All right, go ahead and attempt these. Stop the presentation and attempt these before moving on in the presentation. All right, here are solutions. This number, 5.12500, has 6 significant figures. 5 before the decimal point, so all these numbers after are significant. The number 0.0204 has 3 significant figures. The 2, the 0, and the 4 are the significant digits. This number has 3 significant figures. All 3 digits in the argument of this scientific notation number are significant figures. And likewise, this number has 1 significant figure. This number has 5 significant figures, the 3, the 0, the 3, the 5, and the 0. So if we express it in scientific notation, we must write it this way. All the digits in this number are significant, and therefore all of them must appear when the number is written in scientific notation, like so. Once we've learned which figures are significant and how to count them, we move on to mathematical operations with significant figures. There are 2 rules. One rule for additions or subtractions. This rule is relatively straightforward to understand. In an addition, the sum is taken to the same precision as the least precise number added. So if here, for example, consider the mass of 4 wing nuts weighed on 4 different scales. Here is the mass of nut 1, 7.8456, nut 2, 3.1, nut 3, and nut 4. In each number, I have underlined the uncertain digit. This is the most precise number because the uncertainty is here in the 10,000ths place. This number is uncertain in the 10ths place. This number is uncertain in the 10,000ths place. And this number is uncertain in the 100ths place. If you add all these numbers up on a calculator, you get 22.8878. However, the least precise number is this one, which is uncertain in the 10ths place. This number could be 3.2, for example. If this number is 3.2, the answer would actually be 22.9878 instead of 22.88. In other words, the uncertain digit is not the 10,000ths place, but the 10ths place right here. So the answer should be expressed at 22.9. We round up. Look past the last significant digit. We see a number greater than 5. That means we increase this number by 1. And our answer is 22.9 to the 10ths place. All right. The rules for multiplication and division are somewhat different. In a multiplication or division, the answer has the same number of sig figs as the factor with the least sig figs. So in multiplication, it's important to be able to count the number of significant figures in a number. So for example, if the measured number 22.4 is multiplied by the measured number 3.1, calculator would say 69.44. However, this factor has 2 significant figures. This factor has 3 significant figures. The factor with the least sig figs has 2 significant figures. Our answer has 2 significant figures, which means we have to stop at 69. Now, the digit after the 9 is a 4, which is less than 5, so we round down when writing this answer. Round down means leave 9 as it is. And the correct answer is simply 69. In the event of operations combining multiplication and division, apply the sig fig rules in the order of operations. Let's look at some examples. Here are 6 problems, 5 additions and subtractions, and 1 concerning multiplication. Attempt these, and then move on in the presentation to see the solutions. Here are the answers. When we add 1.3 to 3.964, following the addition rules, we keep our answer to the 10th place, or one decimal place, or 1 place after the decimal point. Similarly, with this number, the least precise number is 193 in the ones place. We keep our answer to the ones place. This addition only allows us to keep our solution to the hundredths place. So I actually write the answer in scientific notation. Likewise, this sum lets us keep the answer to the hundredths place. This sum we keep the answer to the 10th place. And in the multiplication problem, there is a factor with 2 significant figures. This factor has 3, this factor has 4, and this factor has 3. Since the factor with the least sig figs has 2 sig figs, our answer has 2 sig figs, and the answer is 18. All right. It's important to note, when using the addition rules, rules about counting the sig figs do not apply. For example, this number has 1 significant figure, this number has 1 significant figure. Our answer has 2 significant figures. Counting sig figs is not important in additions. Counting sig figs is important in multiplications. Don't confuse this rule, because this rule is because this is where students most often become confused. 1 sig, solution has 2 sigs, and that's okay, because when we're adding, we do not use the multiplication rules. Here are 4 more examples to attempt. All of them involve the order of operations. So in 7, for example, we will take this difference and divide by 1.58. In number 8, we will take this sum and then 4.83 divided by this sum. You should also attempt problem 9, which is an addition. This, and these numbers are all added together. And the solution to number 10 is found by taking this number and subtracting this number. So these are both examples of applications of the addition rule. here briefly are the solutions to the 4 exercises. All right, this concludes the second lecture for Unit 1.